I think we're ready to get started. So we're welcoming Chris Edsall from the University of Bristol in the UK, which is the home of the Isambard Project, which is the world's first production scale ARM-based supercomputer. Chris has a lot of experience in the field. His first supercomputer was an alpha-based Cray T3E. And so we're very happy that he's willing to share his experience with ARM and HPC. Thank you very much, Chris.
Thank you, Kenneth. Thank you for the invitation. So the title of the talk, Yes, You Can Run Your Software on ARM, is the message we'd like you to take away from this talk. And I'll get to exactly who we are in the context of Bristol and the Isambard Project and a couple of other associated HPC projects on ARM later in the presentation. But my name is Chris, Twitter handle HPC Chris, and that sort of gives away the focus of this talk. It's going to be on high performance computing and scientific software running on ARM systems, because of course, you know, software's been running on ARM for decades now. We've all got iPhones or Android or Surface 2 tablets, and there are billions of embedded devices running on ARM, but we're talking about, in particular, 64-bit ARM architecture and HPC software. I just point out that I'm a research software engineer. If you haven't come across that term, that's somebody who has an expertise in software, but maybe not necessarily a particular scientific domain, and partners with domain scientists to bring across discipline from software engineering and to try and improve the quality and reproducibility and sustainability of research software. So if you haven't come across RSE, Research Software Engineering, before, that's a good thing to check out. So today we're going to cover what an architecture is, an instruction set architecture, the ARM architecture 64, some CPU implementations of that architecture, some systems that have been built with those CPUs, clouds, now plural, with ARM, and also where you can get continuous integration systems so you can test the buildability of your ARM software and test the correctness of it, even if you don't have access to the ARM hardware yourself. We're going to talk about some software that's known to work on ARM, the particular SIMD vector instructions from the ARM architecture. We'll touch on the new scalable vector extensions, but by the nature of them being very new, we don't have a lot of results to show there. I'll talk about some compilers that are available that target these ARCH64 HPC chips. But before we get into that, we probably have to mention the elephant in the room. That the picture is an allusion to John von Neumann's curve-fitting elephant. But for this talk, the elephant is the acquiring of ARM off SoftBank by NVIDIA, subject to regulatory approval. But that doesn't look like it's going to hold things up at the moment. For a purchase cost of $40 billion US in some mix of cash and shares, which, because I'm not a high finance mergers and acquisitions person, I don't really follow that. And so the question is, what is this going to do to the ARM ecosystem? And I think that's uncertain at the moment. It's up in the air. A lot of people have opinions, and I think one of the best opinions is we might have to wait and see. So in a couple of slides, I'll get to the business of ARM, and we can see how this might affect things. But that's, since Kenneth asked me to give this talk a month ago, that's one of the things that's changed in the ARM world. To be honest, quite a lot has. But stepping back, what is a processor architecture? So Kenneth mentioned my first supercomputer is on this timeline here, about the green alpha along the top, about the L of alpha from 1999. So I looked after a Cray T3E 1200, and that was made out of DEC Alpha 21264 chips. And we ran that computer for a long time until we eventually replaced it with IBM, which is like the beige, orangey color, second one down on the slide, at about 2010. So until I came to the UK, this was in New Zealand, my HPC career tracked along the top of this graph. But if you have a look at the main body of the graph, starting in about 2000, there were a lot of architectures, and that's been whittled down to just the IBM power at the top, Intel and AMD. And strictly speaking, Intel and AMD are two implementations of the same architecture, the Intel x86 and x86-64. And so in the marketplace, for the last several decades at least, HPC has been very boring. There's really only been one choice, unless you were really weird and bought a IBM power system. You had software running on Intel, or x86 at least, almost certainly on Intel. So what is an instruction set architecture? If you look at the middle box in the top, you'll see a fragment of C++ source code. If you haven't met the Compiler Explorer from Matt Godbolt, the link down there, it's a fascinating resource. What it does is allows you to compile fragments of code with lots of different compilers and targeting lots of different architectures. So on the left, we've got that piece of code which squares an integer, compiled down into x86-64 with the LLVM Clang compiler, version 10. And on the right-hand side, we've got exactly the same source code compiled for a different target with the same compiler, the Clang version 10. And one thing you'll note is that those are not the same. The instructions are different. The order and the number of instructions and even their names are different. So it's imul on the left for Intel and mul on the right for ARM. And you'll notice that the registers have different names as well, RBP, SBP, etc. So this goes to show that an instruction set architecture is one of the points of incompatibility between two hardware systems, and the ISA is really the point of contact in between the software and the hardware. It's the contract between people who write compilers and people who write directly in assembly language and the people who make the chips that those programs run on. And so they have to agree at some point, and where they agree is the instruction set architecture. And so what is the ARM architecture, 64? So as we saw before, it's different to the Intel one. The architecture defines the instruction set, which were those muls and pops and rets, etc. That's called A64. And it also defines how those instructions are encoded, whether it's big endian or little endian, what the registers are, all of the things you need, as well as just the assembly language instructions to make a chip that actually runs software. And so what ARM, the company, does is they provide this definition in an enormously long book, which you can download. And they have various versions of what is ARM architecture. So they're numbered. And so if we're looking at ARM architecture 64, which came in with ARM version 8, you can have version 8.1a, which defines certain sets of registers and certain things, and an implementation of that might be the Marvell Thunder X2 chip. Or they keep on adding things to the architecture, creating new versions. And so an interesting version is the ARM v8.3a, which was the one that introduced the scalable vector extensions, and an implementation of that chip, which you can buy right now, is the Fujitsu A64FX. And ARM have just announced that they're, just a few days ago, that their Neoverse V chips will have the scalable vector extensions. So what does ARM, the company, do, or at least what did it do at the beginning of this month? They license the core designs, the designs for the bits of the cores that go onto the CPU. In the industry, this is called IP. And they will sell those, they will license those designs to people who want to fabricate chips using them. There are a small number of licensees which have architecture licenses, so they've got the permission to go off and fabricate their own silicon with their own core designs. And so it's the licensees who actually make the physical chips that we put in servers and that we run our code on. And it's up to the licensee who's making the system on chip to decide how many floating point units they want, how many memory controllers, what process architecture, what fabrication process they want to use to build these chips, and how they want to pack, how many chiplets they want, whether they want to co-locate the ARM cores with peripheral controllers of some sort, so how the chips are packaged. ARM has a long history, and given that I'm in the UK and my very first computer, so again, I said my first supercomputer was the T3E. My very first computer was that one at the top, the BBC Model B, which isn't an ARM system. It ran on a 6502 processor. But after the success of that, Acorn, the company who made the BBC, made the next one down on the right-hand side. That's the Acorn Archimedes. And rather than use a 6502 or maybe a 6800 or one of the other chips that were available at that time, they actually went out and designed their own, the ARM V1. Originally, ARM stood for Acorn RISC Machines. And it was designed by a very small team. Two of the principal engineers, there's Steve Ferber and Sophie Wilson. One of the interesting things that's happened in retro computing this year is that somebody on the internet has stood up a Twitter bot that you can tweet BBC Basic source code to, and it'll take the code out of your tweet and run it on an emulator of a BBC. Actually, interestingly, a Raspberry Pi, which runs on the ARM CPU. So it runs in the BBC emulator your code and then tweets you back a picture of what happened. And what's the latest development in this series is this chap has come up with the BBC Basic bot, which runs in an Acorn Archimedes emulator. And if you tweet it BBC Basic that would run on an Acorn Archimedes, it will tweet you back the result of that. One of the interesting features of the BBC Basic is that you were able to drop down into assembly language in the middle of your basic program just by enclosing the assembly instructions in square brackets. And so we can see there somebody has tweeted EQUD, adder, mov, SWI, etc. And in the end, that's produced the thing that's cut off at the bottom, that multicolored thing. So if you want to play with some retro computing and in some extremely old ARM version 1, you can do it on Twitter. But back to, more seriously, the high-performance computing processors of today. You can get the Thunder X2 from Marvell. You can get the A64FX from Fujitsu, and as I described before, those run two slightly different versions of the ARM architecture. The company Ampere will also fabricates and will sell you ARM chips. Amazon Web Services have designed their own ARM chip, which they fabricate and then use themselves. They don't sell you the chips, but they do have them in their cloud. The first version of that they called Graviton, and the second one rather unimaginatively Graviton 2. And so for a fraction of a dollar, for a few US cents an hour, you can run on ARM architecture in the AWS cloud. The follow-on to the Thunder X2 was looking exciting from my point of view. And so it was announced in this year's Hot Chips a month before last. But very quickly thereafter, they announced that Marvell announced that it wouldn't be available as a general purpose CPU. It would only be available to customers for the purposes of customization. So you would have to add on the various things and make your own system on a chip. Leaked earlier this month was details from the European Processor Initiative, which is part of the €8 billion HPC joint undertaking. What they've done is they've spun out a company called Silicon Pearl, or SciPearl, and they aspire to make HPC chips of their own. And this was tweeted when some dignitaries were visiting their office, and shows the floor plan of their upcoming processor. The first one is going to be called RIA. It's going to have a mixture of cores, but the CPU cores on the RIA chip, codenamed Zeus, are ARM CPUs, and we found out that these are going to be the Neoverse V1 cores. And so this chip's expected next year in 2021. And the follow-on to that chip is, we know the code name of that already, so the follow-on chip is going to be Kronos, and the CPU cores on that Titan. So that's an interesting one to look out for in systems. Here are some systems fielded right now with ARM HPC chips. So this is from HPE, the manufacturers of the computer. The computer's called Astra, and it's hosted in Sandia National Labs in the US. This is the largest system on the most recent top 500 list, and it's coming in at position 244. Sorry, it was the largest on the previous list. It has of course been gazumped by an HPC system running this chip. This is the Fujitsu A64FX, which is ARM architecture 8.2. It has 512-bit wide SIMD vectors, 48 cores, which are used by the application. So it actually has more cores on the chip, and it reserves some of the cores for running the operating system and the remainder of the cores for the application. The reason for that is you don't disturb the application to run operating system jobs, daemons, etc. And this reduces the so-called operating system jitter, which has a really bad effect on large parallel jobs, because say you're waiting in an MPI barrier call, you're waiting for the last process to hit that barrier. You don't want to keep disturbing the processes and changing the running time. And so that's why the cores are reserved for the application and subcores for the operating system. So this was manufactured on the 7nm process, and they built a lot of these chips and put them into this. This is Fugaku, and this is #1 on the current top 500 list. So it's hosted at the RIKEN Center for Computing Sciences. What we see here is this isn't the whole computer. The slide before, we could fit Astra on the whole slide, but this one is just enormous. So you're seeing just a fraction of the cabinets here. The ones on the right-hand side, the blue bit is the edge of one cabinet with a picture of Mount Fuji on it. The cabinets in the center of the aisle are left blank, so they can actually project things onto the side of the cabinet, which is pretty cool. At a much smaller scale, but maybe possibly more widely available to developers and more pressing, is the fact that Apple has announced that they're going to be transitioning from Intel-based CPUs to ARM, not just in their phones and tablets, but also in their desktop systems. And so if you were an Apple developer, you could have applied to get this, which is a Mac Mini with the iPad CPU in it, the A12 system on chip, to test whether your code would work on ARM. And earlier this month, Apple's presentation, they announced their latest A14 chip, which has 6 cores and is fabbed on the 5nm process. And so, even if you were sitting on the fence about whether you were needing to consider ARM, given that Apple have decided to go that way, it's almost certainly something you should look into. ARM has been known for energy efficiency. It's been known in the embedded space. And so the question is, are these new ARM chips much more power efficient? than the competitors. And this sad news, unfortunate news really is not really. If you pack as many floating point units and as many memory controllers and as many other pieces of CPU architecture into a chip, equivalent to say an Intel chip, you wind up with about the equivalent power. So here's a couple of benchmarks run by the Barcelona Supercomputing Center. You see, going from an older generation Intel system to a newer generation, from the Haswell to the Skylake, you get quite a good improvement in energy efficiency. And then depending on the code, and we'll come back to this later, it's about the same energy efficiency between the Thunder X2 chip, which is the ARM chip, and the Skylake. It's almost exactly the same on the lattice-Boltzmann method benchmark. It does seem that this other benchmark, Dirac, you do get an energy benefit from the ARM chip, but it does depend critically on the code. And so one of the things you can do with the top 500 is you can sort, they measure the energy used, and so you can sort it on that energy usage and come up with a new list, the green 500. So we see here the much smaller cut down test version of Fugaku, the A64FX prototype, is actually number 4 on the green 500 list. Fugaku itself comes in the top 10 of the green 500, which is an impressive feat given how large that system is. And even Astra at Sandian Labs, while it's ranked on the top 500 at 244 for performance, for energy performance, it's up quite a bit further at 172. So we're in the EasyBuild tech talks. We probably have software which we are building and want to see run. And so we say it just works. So I put a little asterisk there because sometimes it doesn't, but for 90, 95% or even more and increasing all the time, it does just work. So if you're building your software from source and it doesn't use any tricky intrinsics, so it doesn't, I'll come to intrinsics in a second, then almost certainly will work. All the interpreters run on ARM64, Python, R, Julia, etc. One of the benefits of these languages is the vast libraries that they have. And so, for instance, a lot of the computing that's done in R is actually done in C++, which is wrapped up into R packages. So I did a test of, so we have a lot of R users at the University of Bristol. And so we wanted to know, could we move them straight across onto the ARM64 machines? And so we got, was it 344 R users that I found on our HPC clusters running more than 1,200 unique R packages. I took the user with the most diverse set of packages, 44 of them, and 42 of them just ran out of the box. One needed an operating system package updated, and the final of the 44th out of 44 was a home-built package which needed some work. But in general, things do just work. In the HPC community in the UK, we're mostly interested in these codes. This data comes from our tier 1 supercomputer called Archer. They're just in the process of replacing that with Archer 2, which will be an AMD box. But the codes that will run on it will be almost exactly the ones that were running when this snapshot was taken in January to March this year. And you see it's dominated by chemistry codes, VASP, CAS, STEP, and CP2K. But rounding out the top 10, GROMACS, LAMPS, NAMD, the unified model from the Met Office, along with the MIT global circulation model, SBLI, and OpenFOAM. and those all do work on ARM, particularly as a result of the Isambard project, which we'll come to. You're probably wondering about what I refer to as the Matlab question. Independent software vendors, if you've got binary codes given to you by a vendor, you don't have the source, you can't recompile it, will that run? That does sort of depend. And so Fujitsu say that they support on the A64FX chip Gaussian, Ampere, and LS Dyna. And so I don't believe the MathWorks have got a public version of MATLAB that's working on A64, as working on ARM architecture 64 yet. But if you want that, you should talk to your ISV and ask. The more people who ask, the more likely it is. So what are some things you do need to care about if you're porting software to ARM? I mentioned if you don't use intrinsics, it's probably just going to work out of the box. If you do use intrinsics, these are the single instruction, multiple data instructions in the chip. So earlier, before we had mul, say, which would multiply two numbers together. What you can do is multiply two numbers with two other numbers in one go, or four numbers with four other numbers in one go. And so these are the SSE instructions, and then later SSE 2, 3, and 4, and the AVX and the AVX 512. So if you see references to those in your code, that's one area you're going to have to pay attention to when you move to ARM. So the GROMACS code got quite a bit of its performance from using intrinsics. So we invited the GROMACS developers along to a hackathon we had a couple of years ago, and they implemented the Neon instructions, which are the ARM equivalent. And now GROMACS runs very well on ARM. Just locally, we had a program called PhiloBase. That didn't need source code modifications. We were able to get that to build just by changing some compiler pragmas. Another bioinformatics code, IQtree, actually had hundreds of instances of calls to the Intel instructions, and those did need to be looked at by hand. There are a couple of libraries which are really handy if you're doing this. One is called SSE, so not libraries, they're header files. SSE to Neon, so you just if-def out the Intel headers, intrinsic headers, and add in #include SSE to Neon.h, or a second project which has quite a lot of coverage. It's called SIMD Everywhere. So both of those are really are useful to look into, because what you can do is you can just change the header file at the top of your source code and leave all the intrinsics as they were, and they'll just get replaced with the equivalent AMD Neon ones. The new thing in ARM in terms of SIMD is these scalable vector instructions. So before, when I was talking about, say, the Intel AVX2 and the AVX 512, the width in terms of the number of bits per operand was fixed. With the scalable vector extensions, what you can actually have is between 100 widths between 128 and 2048 bits. Nobody's built a 2048-bit wide system yet, but the A64FX is 512 bits wide. What we can see here on the screen is, on the left-hand side, we've got the assembly language. This is DAXP, which is one of the BLAS kernels, double precision AX plus Y, so multiply a vector by a constant and add another vector to it. And so we've got the assembly languages on the left. In the middle column, which has got 128-bit at the top, you see the instructions are going, the operands are going in pairs. And if you go down hopefully you can see it, this might be a bit much of an eye chart, but down the gray bit, which is instruction, down the screen, which goes 0, 1, 2, 3, etc. When you hit the LDLD instruction, it splits off into 4 and 11, and then the next instruction 5 and 12. So those will be done in 2 floating point units. Whereas if you've got a 256-bit wide SVE implementation, you can actually do that in the same number of instructions. So you see on the left-hand side, we had 18 instructions to achieve the result. On the right-hand side, just 11 with the wider vector units. Unless you're lucky enough to have access to an A64FX system, you probably can't do SVE for real. You can use a simulator, for instance, GEM5, or the one provided by ARM, the ARM instruction emulator, ARMI. These are good for, so one of the downsides of using the simulator is it's much slower than real hardware, orders of magnitude slower. So you don't generally tend to simulate an entire program, you just simulate the compute kernels, the computationally intensive bit in the middle. And the other thing is they're perfect for verifying correctness of the code under the SVE instruction set, but they don't provide particularly good predictions of performance in terms of cycle time. So at the University of Bristol, when I say we, I'm involved with the operational side of the high performance computing. We have a team in the research side who are looking at writing their own simulator for looking at extensions to both the ARM instruction set and other ISAs. One of the tricks with SVE is you can generate, your compiler can generate instructions that have a fixed width. So the SVE is scalable in terms of what codes can run on the hardware, but a particular code might target a particular width. You can write what's known as vector length agnostic code, or at least your compiler can write it for you. And so the same binary will run on different implementations of SVE with different vector widths. Whether you get VLA, vector length agnostic code, depends. So if the Fujitsu compiler, because it targets their chip and only their chip, which has only 512-bit wide vectors, assumes that. The Cray compiler will generate fixed width, but you can give it a compiler flag to specify that you want VLA. The ARM compiler is the opposite way. Well, the ARM compiler does VLA only, and GCC can do both, but defaults to VLA. So this is probably not a concern right now, but it's something to look into in the future as these SVE chips become more widespread. So if you are porting to ARM, there's a bunch of resources. The obvious one to start with is ARM themselves on their websites. They've got quite a lot of useful information. The best site I found that ARM provide is the ARM HPC Wiki. And so that's got programs that they've compiled themselves and they know work, or various sites are compiled. You probably can't see in the small blue writing, but there's the RIKEN list there. There's a list of the Isambard list, the list that we've provided of codes that work. And of interest to this talk, you'll see that the columns are headed up, compiles with ARM compiler, compiles with GCC, and is there an EasyBuild package for it, and is there stack support? And so one thing that would be good is to maybe get a few more ticks in the EasyBuild column. But it does have, this website has the instructions for building those particular codes by hand. What compilers can you use? So any recent version of the free and open source compilers, GCC and Clang will target ARM Architecture 64. ARM have their own compiler. It's available for a 1-month trial download, but otherwise it's licensed. That one is based on Clang. Cray have their compiler. They, of course, have a long history of HPC and software development and compiler development. And so they had the Cray Classic compiler. They've since moved to an LLVM-based system, a Clang-based one. But it does have the Cray front end to it. So there's a mix there. Fujitsu have a compiler, as we mentioned before, that targets the A64FX chip that they make. And NVIDIA, a while ago, bought the Portland Group, who made the Portland Group compiler, the PGI compiler. And they've rebranded that this year and made it free as in beer download. It's named the NVIDIA HPC SDK. That one's quite useful because it supports x86, 64, and Power, and ARM. Which compiler should you choose? Well, your mileage may vary. So this is a paper from the HPC researchers at Bristol I mentioned before, the group led by Simon McIntosh Smith. This paper of theirs from 2019. So if we redid this today with newer compilers, you see along the bottom, we've got GCC 8.3, and we'd probably use 10. We'd probably use 20.3 came out earlier this month, and the Cray compiling environment is now onto CCE 10. So hopefully that would clean up some of the red build failures in that table. But if you look at the green, which is where the program is compiled and ran, which compiler gave you the best runtime performance depends on the code. So if you're running Cloverleaf, which is not a real application, but a mini application, a stand-in one, so slightly larger than a synthetic benchmark like Stream or LinPack, but much smaller than a big application. So if you ran Cloverleaf, you'd want the Cray compiler, otherwise you'd be giving up 27% performance compared to GCC. Whereas for T-Leaf, which is also a mini app, it's the opposite way around. You want the Cray, you want GCC rather than Cray. So if you have access to multiple compilers, you should definitely try the same code out on all of the compilers you have access to and see which gives you the best result. So I said it just works asterisk because of a great deal of effort by people around the world at sites like ours who have ARM systems, plus ARM themselves. A lot of the problems have been shaken out already, and now we're just tracking down the really obscure ones. So this was tweeted out earlier this month. A Python wheel, so PyPI is the Python package index. Python, of course, is an interpreted language, but there are some libraries which contain compiled code, and you can either download the source for that, or you can download a binary built package, which is known in their terms as a wheel. And so one of the problems they encountered is that the huge page size on a particular Linux distribution is not fixed like it would be on x86. And so that they had alignment issues with the binary wheels that they were building on one page size and then trying to run on another. And so the good news is, I just did the screenshot today, 4 days ago, they've closed that bug. So that's the scale of the issues we're getting down to. It's getting pretty obscure. Most of the software does just work. If you don't have enough money to buy a whole HPC cluster, but you can afford a few cups of coffee, you can buy ARM in the cloud. Already mentioned was Amazon Web Services with their Graviton implementations. And the Graviton 2 is a really price-performant piece of kit. So what we're looking at on the left here is a graph of the price performance of a weather code. So WRF, the Weather Research and Forecasting code, one of their benchmark cases is the continental US at 12-kilometer resolution. And we're looking at cost to solution here. So it might be slightly slower to get your answer on a Graviton 2, but much cheaper. So depending on what your workload is, it might well be worth checking out Graviton 2 as a platform. If you go to Amazon, they will give you a console and a bewildering choice of things to click on, VPSs and EC2s and S3s, etc. If what you want is something that looks almost exactly like your institutional HPC cluster, one of my colleagues, Matt Williams, has developed this, the cluster in the cloud, which presents you something that looks like a Slurm cluster, a node that you can log into and submit jobs. So it's made out of Terraform and Ansible. We support currently Amazon Web Services, Google, and Oracle. And that's one of the ways you can get a cluster running Graviton 2. So rather than just a single EC2 instance running Graviton 2, you could have as many Graviton 2s as you can afford. And so the concept is you go to that URL, clusterinthecloud.readthedocs.io. You step through the process, which is git clone a repo, edit the credentials for your Amazon account, run Terraform apply, go get a cup of coffee because the next step takes about 5 minutes, SSH to your login node, and then you can run EasyBuild. In fact, there's a step that's missing there, is you would configure how many nodes maximum you wanted your cluster to be. And I would recommend using the EasyBuild functionality that allows you to submit jobs to a queue, because the login node in the cluster in the cloud is always an Intel node, even if your compute nodes are ARM. And of course, the login node is quite small, and you can have arbitrarily large, but very large compute nodes to make your easy builds faster. And so here's an example. The login node is also the management node, which is why the prompt says MGMT. srun is how you get an interactive job in Slurm, srun minus I. And I'm just specifying there in the constraint field that I want shape, and that terminology comes from the fact that we built this on Oracle first, and they call their instance types shapes. We're specifying a shape of C6G4X large, which is one of the AWS Graviton 2 instant types, and running bash. And down below, you'll see that we now have 2 instances, one called MGMT and another one with the prefix robust duck, which just happens to be in this particular cluster because we're using the pet name functionality to generate a unique name, so that you can run multiple clusters with multiple management nodes and multiple file servers, and the names don't collide. So I can definitely recommend Cluster in the Cloud if you want to run in Graviton, if you want to run a cluster in Graviton 2 in AWS. I should point out that AWS have their own cluster solution, pCluster, but Cluster in the Cloud got there first for Graviton 2. I said earlier that there are clouds now. It's possibly getting a bit ahead of ourselves. But last week in the Oracle Cloud HPC announcement, they mentioned that they are going to be providing CPUs from Ampere. In the first instance, there'll be dual socket nodes with 80 cores per socket, and Ampere are talking about a pin compatible upgrade from the 80-core chip to 128-core chip, and Oracle are saying that this will be available in the first half of 2021. If you have a piece of software and you've got your source code somewhere that your continuous integration can get at it, there are now options to run builds and tests. So Travis did have an option to run in QEMU systems, so emulated on top of x86 to test ARM, and that was super slow. So they now have an implementation which uses the AWS Graviton 2. If you have GitHub Actions, you can run a self-hosted runner on ARch64. and the same with GitLab and BuildKite. And actually, there are a plethora of continuous integration systems. Well, not anything that allows you to run your own runner, but a lot of them, if you run your own runner, you can do it. But Travis, you can use the AWS ones. If you do have money for your own HPC cluster, HPE will sell you an Apollo 70 system. And so these are based on the Marvell Thunder X2. And they're connected together with InfiniBand. They partnered with the UK academic community at 3 sites, Bristol, we were one of them, along with Leicester and Edinburgh. So they deployed these systems in those universities for us basically to shake them down, to find the issues with the software stack. There weren't many. And so it's to make that a viable product that HPE could go out and sell to anyone. And so at the Bristol one, at least, I can't speak for the Leicester and Edinburgh Catalyst systems, but on our Catalyst, we were keeping the software environment very stock. So pretty much exactly what HPE would deliver if you bought one. So that's the ARM compiler, but we have GCC available with the ARM performance libraries and HPE's message passing toolkit as the implementation of MPI, but you could use OpenMPI as well. So we've got one of those systems running at Bristol. And this was the reason Kenneth invited us to talk, because we made a big splash a couple of years ago with the Isambard project. So Isambard Kingdom Brunel is a bit of a hero engineer in these parts. He's the chap you can see on the front of the cabinet in the black and white photo with the enormous top hat, standing in front of the chains, which were part of the ship, the SS Great Western, as well as the Great Western and the Great Eastern. He made the Clifton Suspension Bridge in Bristol, which at the time was the largest suspension bridge in the world. And he built the railways that joins Bristol and London, and the railway stations all along the way, and bridges, etc. So great deal of engineering works in this part of the world. And the GW4 consortium of universities is named after the Great Western, and the universities are Bath, Bristol, Cardiff and Exeter. Together with the Met Office and Cray, we put together this project, Isambard, to see, because at the time people were a bit reticent about procuring a large HPC system, because it hadn't really been proven in the field at real scale. So trailblazers like the Barcelona Supercomputing Center with the Mont Blanc had smallish systems, but what we really wanted was something with 10,000 cores, supporting real workloads. So we targeted the Archer top 10, and we ran hackathons. We invited software developers to, and this was before coronavirus happened, so you could all meet physically in the same room, to get together in the room and hack on the applications themselves, and the compilers and the profilers and the debuggers, etc., to make sure the tool chain was rock solid, and that the applications that we wanted would run. And the other goal of this project was to demonstrate this running in production. And so we've had this running for several years now, more than 400 users from the UK academic community and around the world. And so I think the answer to the question, can you run an HPC system on ARM, has been fairly comprehensively answered by that. What does the, if you're building software, what does the environment look like on a Cray? I guess compared to a tool chain in Isambard, the Cray concept is a programming environment. So you log in and you choose your programming environment. The default one's Cray, but you can switch it using the modules to Alinea, which is their name for the ARM compilers and the ARM performance libraries, or switch it to GNU. no matter which one you choose, you always call the C compiler lowercase cc, the C+ compiler uppercase cc, and the Fortran compiler is always called ftn. And then it goes through the various wrappers and ensures that you get well, it doesn't ensure you get a successful build. Hopefully you get a successful build. So what does this look like? Here is some software that we've built. I hesitate to say not using EasyBuild. We've built these all manually, but we feel the pain of that and are looking at solutions to automate it. So down in the middle column there with the applications, these are ones that were built by us for the users who don't want to build their own software. We do actually have a lot of users who do build their own, so there's way more software than that available running on the system. And on the right-hand side, that's just the QStat, no, that's APStat output. We can see that at the time of that snapshot, we were running ChemShell, MD-Run MPI as GROMAX, VASP, not sure what the various size Python 3s were, lots more VASP. More Python from a different user, more VASP, more Python, CP2K. And so that's just a day in the life of Isambard. It's busy doing production supercomputing on ARM. So that project was successful enough. We were funded to expand it to Isambard 2. So we've taken the Cray XC50 and put a second cabinet on it. I would, on the right-hand side of the slide, show you the cover, the rack cover art. Unfortunately, it's embargoed for a press release, and we haven't made the press release yet, so you can't see the cool picture we put on the front cover of the racks. As well as doubling the size of the existing system, we're adding in 72 A64FX nodes. And so before I mentioned the HPE Catalyst system is called also known as the Apollo 70. This is the follow-on product is the Apollo 80. And so that's the same processor that's in Fugaku. And we've expanded we've got a small bit of hardware on the side for the multi-architecture comparison system, where we have a few nodes of AMD Rome, Zen 2 based, some Intel Cascade, and some NVIDIA V100s. So if you are part of the UK academic community, you can access Isambard. If you go to the Isambard docs website, it's got the instructions for how to apply for an account. It's basically the same as any of the other tier 2 systems in the UK. You get yourself a safe account. You can apply for allocations on Isambard. So we'll give you an account and you can test the porting and do small scalability runs. But if you need a large amount of computing resource, you can go through the EPSRC's, what used to be called the Resource Allocation Panel, the RAP, is now the Access to HPC process. If you are a developer from a package, an open source package, and you would like a scientific package that you would like to see run on ARM64, you can get in contact with us as well. So the same way we did the hackathons, which include the developers of GROMAX and VASP and OpenFOAM and OpenSPLI, we're going to be running hackathons again on Isambard 2 for the A64FX, and we'd be happy to receive applications for that. So I keep on saying we, and here are some of the people who've contributed to the results that you've seen in this talk. So the research group led by the Simon McIntosh Smith, including James Price, Tom Deacon, and Andre Pinero. Joe Heaton, who is the sysadmin at the Met Office, who keeps Isambard ticking over. The other members of the GW4 consortium and the Isambard partners, the research software engineers and ops teams, Cray as was, HPE Cray as they now are, Amazon Web Services for the access to the Graviton systems, and my colleagues at the University of Bristol in the Advanced Computing Research Centre, so our director Simon Burbidge, and colleagues in my team, the Bristol RSE, including Matt Williams, who wrote The Cluster in the Cloud. So things are changing fast in the ARM world. I've had to change these slides every week for the last 4 weeks as new things have been announced. You can run your HPC code quite fast on ARM CPUs, as fast as any other CPU. And in particular, if you're looking at Graviton, they're very price performant compared to other architectures. Your software will almost certainly work. If it doesn't, we may be able to help, or do log a bug on the GitHub or whatever the source control system for the project is. And I recommend you give it a go. There's no reason not to. And now I'll open it to questions.
Okay, thank you very much, Chris. So if anyone has questions, please share them in the Slack channel, the EasyBuild Slack channel. We have a Tech Talks channel there. So some people have been raising some questions during the talk. There was one actually right before the talk, which I think you still caught, Chris, about the floating point exceptions.
Yes, so so what I'm going to do is I'm going to hang around in the Slack channel after we finish the stream today, and I'm going to answer the tricky questions that I can't do off the top of my head. Off the top of my head, I think the answer to that question is the only mathematics exception flag that's different between x86 and AArch64 that might trip you up is something to do with integer division by 0. That's off the top of my head, and I'm going to have to verify that. So I'll dig that out and put that in the channel.
Okay, cool. There was a question by Thomas Green about the difference in numerics for R packages, if you've seen some issues related to that. So in terms of numerical accuracy when building on ARM versus building on x86.
I haven't. When I did the survey of R packages, I just ran the build and install thing. To be honest, and I will have to hand in my RSE card at the end of this talk, I did not run the tests separately. So I ran whatever tests were in the normal installation process, but I haven't seen that difference. So if Tom can point one of these out, I would be very interested to know, because while things will not be identical bit for bit, this is the sort of the nature of the floating point maths. They should be equivalent within some epsilon, which you would have to define maybe on a package by package basis. It's a philosophical question: are these two floating point results the same? And bit reproducibility is easier to achieve within one architecture than across architectures.
Yeah, it's true. Since it's floating point, it's never exactly the same, of course, but it has to be within certain bounds. But it seems like there's no known big issues with that on ARM compared to x86. That's very good.
No, so what I'm basing my answer there on is the larger packages. Like GROMACS is a good test of the floating point. If you got different answers in GROMACS, there'd be a real problem, but we don't. And we don't get different answers in OpenFOAM and things like that. So there are other software packages that we've run which give the equivalent answer between x86 and Intel. So the answers aren't wrong, but they might not be bit reproducible, bit identical, but they're not wrong.
Yeah. Okay, you show the matrix of applications and compilers, where I noticed that Snap was, when compiled with GCC, was quite far behind. Compared to the Cray compiler here. So it was only reaching 58% compared to the Cray, and the ARM one crashed, so that's not very helpful. But do you know where the big difference comes from? What is the GCC compiler not doing that the Cray compiler is, or?
Given that amount of performance difference, it will be not vectorizing some loops. It will be, and because Cray has a long history of Cray compilers and software have a long, and toolchain have a long history of different architectures going back to when Cray actually had vector supercomputers. They paid a lot of attention to vectorization and heuristics to look at loops in source code and see whether things. So the issue with the vectorization is it's very, very easy to say, oh, this loop looks like it could be vectorizable, but I'm not absolutely sure because I'm using C, or C is the biggest culprit. Because I'm using C, I can't be absolutely sure of the safety of the values inside the loop. I can't be sure that they're not going to be changed by something else. So the compiler doesn't have enough to go on to be sure that it's safe to vectorize, so it doesn't. And so those heuristics and those rules are probably better developed in the Cray compiler. So that would be my guess. So this is Bristol research, but it's again the research group, not the operations group. So the paper is there. The paper is from last year, from 2019, and you'll note the compilers. There's the ARM compiler 19.2 and GCC 8.3. If you're going to redo this today, you would use GCC 10, and you'd use ARM 20.3 and Cray CCE 10, and you'd probably find all the red will have gone away, and the difference in snap may well now be better. I couldn't tell you for sure that it is, but that's probably what it is. So my guess is older Cray compiler playing on the safe side and not vectorizing a loop, which the Cray compiler could.
Right. Yeah, but based on this, I would conclude that the first pick should probably be GCC as a compiler, because you have a pretty good chance to actually get it running, which is the first step, right?
Yeah.
And then if you really care enough about performance, or it's a big enough application, then it may be useful to look at some of the commercial compilers out there. Or I guess Clang should be included in this overview as well as an open source alternative, maybe. Yeah. Okay. Yeah, there was the question in the chat about the build and the crash, but I guess the build is a compile time issue and the crash is a runtime problem. Yeah. All right. Let's see what else. There was a question on bioconductor. So the bioconductor R packages we've been playing on, or some of the easy builders have been playing with bioconductor on ARM recently, and there were several R packages there that were problematic, which was a lot less the case with standard R packages from the CRAN repository.
Yes, and I noticed somebody else in the chats mentioned RAXML.
Yes, yeah. Well, that was actually unrelated, but yeah.
Yeah,
but I guess this one has a lot of intrinsics as well. Or...
Exactly. So that did seem to be the fashion in the bioinformatics code, because your G's, A's, T's, and C's are easy to squash up into vectors and operate on in wide vectors. There's a lot of intrinsic use in the high performance bioinformatics stuff. So that doesn't surprise me that the ratio of things that work out of the box is lower on bioconductor. So that would be a find the ones that don't work and raise an issue in their GitHub.
Okay, let's see what else. There was a question about ARM Fortran compilers as well. So it seems like there is a Fortran compiler as a part of the ARM compiler suite.
Yeah, so there are two at least. There's old Flang and new Flang.
Okay, and is the new Flang already part of the standard CLang distribution, or is it still in process?
Yes, so I'm just thinking. Yes, so if you grab the ARM HPC compiler off the ARM website, that includes C, C++, and Fortran.
Okay, but maybe that's something they add on top of a standard CLang. Okay. And then the question I had is you mentioned the different compilers, and this is a very good example of what you may be running into. But what about important libraries, low-level libraries like OpenBlast, for example? Have you looked at how open source libraries like OpenBlast and Bliss compared to the ARM performance libraries, or what are the ARM performance libraries based on? Is it in-house or?
Jörg asked me this before, so I was anticipating, in particular he asked about the ARM performance library, and I did a bit of Googling about that and couldn't find the answer, so then I ran strings on the .a file, and NAG popped out. So I suspect that the ARM PL is based on the NAG library.
Okay.
Have we looked at performance? Basically, what I advise when I'm building software is that you stick with the library that goes with the compiler. So if you're running the Cray compiler, the Cray compiling environment, you use the Cray libsci. If you're running the ARM compiler, you use ARM PL, and GCC. You could use
anything, right? Yeah.
FFTW3.
Yeah. There it really depends, I guess, on how mature those are on other architectures like ARM or Power.
I should say, if you are interested in this, follow up some of the links in the presentation, the papers, because there is quite a community of people who are running these benchmarks. So one of the things is I'm coming at it from a more operational, how do you run a cluster and get users on and get them running jobs, rather than this particular library, what's the performance characteristics of that. So there are other people who have looked into that, and those results are available.
Yeah, there's some questions now about bigger applications like CP2K and GROMACS and VASP, but I think the Bristol group has some papers on this as well, right?
Yeah, so running a tool or the performance of them.
Yeah, mostly like how do they perform, just the raw numbers in terms of speed, and not just the cost aspect of it, but also do you actually get close to what the recent Intel processor gives you in terms of performance, or do you really have to factor in cost to be competitive? I guess that's also part of the...
Yeah, so socket for socket or node for node, the ThunderX2, so all of the benchmarking we've been doing on Isambard 1 and the Catalyst have been on the Marvell ThunderX2 chips, which are like the graph I showed for the energy. They are, pretty much ballpark the same as Skylake. Mm-hmm. So they came out at about the same time. So they're about equivalent performance. And so
I think some of the recent numbers that Fugaku has come up with also show it's really good. At least the Fujitsu processors are very competitive.
Exactly, and so then it comes down to a price performance argument. And at the time, the ThunderX2 chips were selling for a lot less than the Intel chips were. Mm-hmm. What Fujitsu are charging for the systems, I don't actually know. But that is one of the things. I mean, we in Isambard 2, we physically have our A64FX nodes, but they haven't been handed over to us yet, so we actually haven't been able to run on the real silicon. But we'll know that shortly, and we'll be very interested to know what the difference in performance versus Intel and Power and RISC-V.
Yeah. And I guess another thing to look at is the amount of effort that you have to spend to actually get it running. So that's the first step.
Exactly. And I think thank you for the invitation to give the talk. And one of the aims of this talk is to say, don't be afraid of it. It's not that much effort. It's really not that hard, unless you've got a lot of intrinsics already in the code. Yeah. And you might be lucky there in those cases that the header files SSE to Neon and SIMD everywhere might get you over that hurdle of at least getting it running, and then you can then you can profile it, and then you can look at the bits that might need tuning for the architecture.
Yeah, that's also the experience we got in the last couple of days and weeks with playing with EasyBuild on top of ARM, where we saw GROMACS and OpenFOAM, and any dependencies you need are really no issue at all. And I guess that's a big reason of that is the Isambard project, where there was a lot of effort spent on porting these bigger applications. Yeah. Okay, good. It looks like we're slowly running out of questions in the Slack channel. So unless somebody else has a burning question right now, I think we can wrap it up here. So the slides are available on the event page, and the recording of the talk will be available on YouTube as well. And with that, thank you very much, Chris, for making the effort. I think it was a really good talk, and it will be really interesting for people to get a better view on how ARM is doing in HPC and why NVIDIA is willing to give that amount of money for this.
Indeed.
Okay.
Thank you.
Thank you very much.